Hello students, welcome to video lesson 8.3a. First half of the video lesson we're going to do on trigonometric ratios. Okay, it's always a fun word to say. You can try it yourself. Trigonometric. Trigonometric. We say trig for short, but we're going to talk today about the trigonometric ratios. Okay, the first three, the more basic three trig ratios that can be used and where they come from and what we can do with them and so on, okay? So this is just intended to sort of be an introduction to them, but we will talk about them in terms of right triangles, okay? So in previous videos and in previous courses, we've talked about the relationship among the three side lengths of a right triangle, right? The Pythagorean theorem. But in a right triangle, the side lengths also have relationships with the angle measures, okay? So for a specific measure of an angle in a right triangle, the ratio of the side lengths to each other is always the same, okay? And these ratios are called trig ratios, right? So our definition for now of trig ratios is just ratios of the side lengths in a right triangle, and I should say in here for a specific angle, okay? Or for a certain angle, for a certain angle. All right, so if we look at this example, this right triangle here, I labeled for us the angle x degrees. Okay, so this is sort of the angle that we're going to talk about. Angle x, we'll call it. Okay, so for angle x, each side of the right triangle has sort of a special relationship to that angle x. Okay, so there's still such a thing as a hypotenuse, right? In a right triangle, across from the 90-degree angle is always the hypotenuse. Okay, so the hypotenuse is always going to be here. It's never going to change. But because of where I've put my angle x, the angle that I'm talking about, the angle in question here, if I go all the way across the triangle from that angle, I arrive at what we call the opposite leg, okay, or the opposite side. So we talk about the opposite leg or opposite side, and then the other leg of the right triangle is called the adjacent leg. Okay, so we still have our hypotenuse. For whatever angle you're talking about, you then have an opposite side all the way across, and you have an adjacent leg, which is right next to it. Okay, so there's opposite leg or opposite side. There's adjacent leg or adjacent side, and the hypotenuse. Those three names or classifications, I guess you could say, for our side lengths in a right triangle are how we define our trig ratios, okay? So we have opposite, we have adjacent, we have hypotenuse, okay? Opposite, adjacent, hypotenuse. Those three names for our side or classifications, as I said, for our side lengths. Now we have three trig ratios, and they are listed here for you. They are the sine fraction, the cosine fraction, and the tangent fraction, okay? So I want you to notice that over here, they are all ratios or fractions. One number, one side length on top of another side length, okay? So they're always fractions or ratios. Hence, that's why we call them trig ratios, right? So the sine ratio is abbreviated SIN, okay? And that is defined as the ratio of the opposite side from the angle you're talking about over the hypotenuse of the triangle. Okay, so it's the opposite side over the hypotenuse. Opposite over the hypotenuse. And then the cosine fraction still has the hypotenuse as the denominator of the ratio, but the numerator is now the adjacent side. Okay, so the cosine, which is abbreviated COS, cosine, is equal to the adjacent leg over the hypotenuse. That ratio, the adjacent leg over the hypotenuse, okay? And then the tangent ratio, or the tangent fraction, does not involve the hypotenuse at all. It's the opposite leg over here, over the adjacent leg. Opposite over adjacent, okay? Now, there are a couple of ways that we can try to remember these. Of course, I hope and expect that they will be in your notes, that you're writing them down now, what the sine is equal to as a ratio, what the cosine is equal to, what the tangent is equal to. But if we look over here at this giant acronym, which we can read it as SOHCAHTOA. SOHCAHTOA. Okay, so I sort of remember that by like thinking about going into a hot tub, right? What do you do before you get into a hot tub? You soak a toa, right? You soak a toa in the water just to see how hot is it. Is it really hot? Is it not so hot, right? Okay, so get in a hot tub, soak a toa. So SOH, this first three letters of my acronym, they stand for the sign ratio or the sign fraction, okay? And they tell me that the sign, right, the sign is equal to the opposite over the hypotenuse. Okay, so that's what the first three letters stand for. Sine, opposite, hypotenuse. The second three letters stand for cosine, adjacent, and hypotenuse. And then the last three are tangent, opposite, over adjacent. Okay, so we have sine is equal to opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. Again, so S-O-H, ka, C-A-H, toa, T-O-A, all right? Another way, if you prefer more of a joke method, more of a humorous remembrance, I guess, besides soaking a toe in the hot tub, each of these letters can stand for a word in a little story, okay? So we can also say, some old hippie caught another hippie tripping on acid, okay? So there's just, minor drug references for you. Some old hippie caught another hippie tripping on acid. If you can just remember what those words start with, some is S, old hippie, O-H, opposite hypotenuse. Caught is a C, another hippie, A-H, adjacent hypotenuse. Tripping on acid is T-O-A, tangent, opposite, and adjacent, okay? So we have all these different ways we can try to remember what side lengths each trig ratio is going to be defined as, okay? And that's going to be helpful because we're going to need to look at a triangle and decide what information do I have? What two side lengths do I know in terms of the angle? And then figure out which of these three trig ratios am I going to be using in this problem, okay? So here's sort of what we're going to have to do in our homework, all right? So here I have a right triangle, labeled my corners A, B, and C, and I have labeled the side lengths as well, 9, 12, and 15. You can double check those. That is a Pythagorean triple. It's a 3, 4, 5 times 3. So I can write fractions now, or ratios, and then of course reduce them if possible for the sine, the cosine, and the tangent, okay? But it is important always to notice what angle are we talking about for that particular ratio, okay? So in this first case, first thing that I'm being asked to find is the sine fraction for angle A, okay? And the sine fraction of angle A, well, we first have to identify where is angle A in my triangle? Well, it's right here. So angle A down in this corner, if I want the sine fraction, what two sides do I need to write the sine fraction or the sine ratio? Well, sine, so S-O-H, right? Some old hippie. So O stands for opposite, H stands for hypotenuse. So opposite side from angle A. What side length is all the way across from angle A? Well, all the way across would be over there. So that's 9. So my top number, my numerator of my fraction is going to be 9. The denominator is going to be the hypotenuse because of the H. So that's, across from the 90-degree angle makes 15. So 9 over 15 can be reduced by 3, I think down to 3/5, right? Divide top and bottom by 3. We get that. So 3/5 is the ratio of my opposite and hypotenuse sides, right? So we would say that the sine of angle A is 3 over 5, okay? What about the cosine of angle A? Well, the cosine, remember, cosine is ka, right? So ka toa. If I think middle three letters of my acronym, C-A-H. So ka toa. So C-A-H. Well, cosine is then adjacent side over hypotenuse. Adjacent side is going to be here, right? The one that's not the long one, but the leg, the shorter of the two, or the two shorter ones, that's close to the angle I'm talking about. So angle A is here. The adjacent side is right next to it. So it's 12 in this case. So 12 is my adjacent side. And then 15 is my hypotenuse still, right? And cosine still has a hypotenuse on the bottom. So 12 over 15 can also be reduced down to 4/5, dividing them by 3. And the cosine then of angle A is 4 over 5. Okay, the cosine is 4/5. And then the last thing I'm asked to find is the tangent of, now they've switched it up on me, right? Now they want the angle C. So if I go to angle C, which is now up here, of course, angle C, and I want the tangent fraction, tangent TOA, TOA, T-O-A, opposite and then adjacent. So top number is opposite side, bottom number is adjacent side. But now remember, I have to find the opposite side for the angle that they are asking for, right? So for angle C, what is the opposite side length? All the way across the triangle is 12. So I go 12 over, and then my adjacent side right next to C, not the long one, but right next to my angle here is 9. So the adjacent side is 9. And again, I can divide both of those by 3, and I wind up at 4/3. So the tangent fraction for angle C is 4/3. Okay, that's different than the tangent fraction for angle A. If you want to, you can pause and find the tangent fraction for angle A. Right now, it's similar, but different, not the same thing at all, okay? So we can always find sine, cosine, or tangent fractions for either of the two angles that are not the 90-degree angle, okay? That's important. We are not going to find sine, cosine, and tangent fractions for the 90-degree angle, because if we try to do like opposite side over hypotenuse, the opposite side from angle B is the hypotenuse. So opposite and hypotenuse, they'd be the same thing. So anyway, we can't do it, okay? I mean, we could, but we are not going to do it in this video. Sine, cosine, tangent, we can find for either of the two angles in a right triangle that are not 90 degrees, okay? So that's the first thing we have to do, is we have to be able to find the fractions, okay? Now, if we know the measure of the angle in the triangle, then we can find the value of any ratio, and we can actually use that then to find missing sides of a right triangle, okay? So it becomes another tool for finding missing sides, particularly if we're missing two sides of a right triangle, but we happen to know one of the angles, we can find those missing sides, okay? So here's what I mean. If I look here at this trig ratio, the sine of my 35-degree angle, in this triangle, here's my 35-degree angle. The sine of my 35-degree angle is, I can find it as a ratio of these three sides, right? It's the opposite side over the hypotenuse. Again, sine is opposite over hypotenuse. So SOH, some old hippie, right? Okay. So for my 35-degree angle, what is the opposite side? Well, the opposite side in this case is X. Right, and what is the hypotenuse? Well, my 90-degree angle is here, so my hypotenuse is Z. So the sine of 35 is X over Z, X divided by Z, whatever that is, okay? Now, the interesting thing is the sine of 35 degrees, it doesn't actually matter how big or small the triangle is. If that angle is 35 degrees, the ratio is always the same. So we can actually use a calculator to find a decimal version of the sine of 35 degrees, of this ratio that I don't know either the top or bottom. But because I know it's the sine of 35 degrees, I can find the decimal version, okay? Now, one option, you can just Google it, okay? You can Google the, like a calculator, or maybe even use it. I don't know if it'll be on your calculators on your Chromebook, but certainly if you have a calculator that have any of these three buttons, sin, cos, tan, you can see them there between the pi and the divide. Okay, normally like 1 or 2 rows above the 7, 8, and 9. If you have buttons sin, cos, and tan on your calculator, you can find the value of any trig ratio, okay, for a certain degreed angle, right? So one thing that, if you do have one of these calculators, I want you to try right now doing the sine of 35. So hitting the sine 35, okay, sine 35, hit enter. It should come out to be 0.573576. Okay, so this should be equal to 0.573576. If it's not, your calculator is probably in a different mode, and you can find a mode button and change it to degree mode. If you need help figuring out your calculator, specifically doing these sines, cosines, tangents, do please let me know. Okay, I want to help because these are going to be crucial to what we're going to do now. Okay, if you are using your phone, you should still be able to find sine, cosine, tangent if you tip it on the side and get all that extra stuff on the phone. If you're struggling to figure out how it works on your calculator to do the sine, cosine, or tangent of a certain number of degrees, please reach out to me. Super, super important. Okay. Now, once we have the sine of 35 as a decimal, okay, let's change things around. Let's say this is not z, but I actually know how long my hypotenuse is. Okay. I know that the hypotenuse in this case is like 8. Okay. Hypotenuse is 8. So now this sine of 35 is not x over z anymore. Now it's x over 8. Okay, x over 8. And I can actually use this equation because now I just have one variable, right? I can solve for that variable and I can find exactly what the what the side length x is in this particular triangle. The way that I do that generally is I convert the sine of 35 to a decimal. Okay, and as we're doing this, if you round off too much, you're going to get an incorrect answer. So I always try to take 4, 5, 6 decimal places when I first do that sine, cosine, or tangent on my calculator. Then at the end, I can round off to 1 or 2 decimal places. Okay, and I'll show you that in just a minute. But I get my decimal version and I set that equal to x over 8. Okay, and then I put the decimal version over 1, and I've set up what we call a proportion, which hopefully we remember. We've done proportions kind of a lot, right? We've done them all throughout chapter 7 with our ratios, our similar triangles. So we have a proportion here now, and we can solve this, right? We can solve by cross multiplying. We can solve by the fish method if you want. We just end up doing, in this case, 8 times 0.573576. Right, and then divide by 1, right? So, okay, so this is what I'm doing now. I don't know if you guys can see that. There we go. Right, so I'm doing that decimal version, or 8 times that decimal version, then divide by 1, hit enter, and I get my value for x is 4.5886. It's about 4.59 or approximately 4.6. Okay, so that side length here has to be the side length because that's the only way that 4.6 about divided by 8 gives me the correct sine ratio, okay? Because I know from my calculator that the sine ratio is supposed to be 0.573576. So I use what my calculator tells me the sine of this angle, what this angle means for a sine ratio, and I use that to find my missing side, okay? So if we look at just a couple more examples of that. Here's one where I have an angle 64 degrees, and I'm trying to find the side length A. Okay, so now this is a situation, again, where it's important to have your notes or to begin to sort of memorize your sines, cosines, and tangents in terms of what side lengths you need. Okay, so let's talk about this 64-degree angle and what side lengths do we have like labeled in our picture for that 64-degree angle. Do we have the opposite side labeled with anything, a variable or a number? No, we don't. So we're not going to use the opposite side at all. We do have a variable on the adjacent side. Funny enough, it happens to be A on the adjacent side. And then we have a number on the hypotenuse, right? So I know the hypotenuse, and I'm trying to find the adjacent side. So that's AH. A and H is the middle 3 letters, right? Ka, caught another hippie. C stands for cosine. So again, I'm using sort of my acronyms and my notes to figure out for my 64-degree angle, what information do I have? What trig ratio can I set up here, okay? So I can set up the cosine ratio for my 64-degree angle, okay? Specifically, I know it's equal to my adjacent side, which is A, over my hypotenuse, which is 28. Okay, and again, now I have set up sort of what I had before. I'm going to use my calculator to do the cosine of 64 degrees. Cosine of 64 degrees is about 0.43837. So the cosine 64 is 0.43837. That's equal to A over 28. I put that decimalized version over 1, and again, I have a proportion, right? I can cross multiply, so I can do, 0.43837 multiplied by 28, and I get about 12.27436. And then the other one is 1 times A, so 1 times A doesn't really mean anything. 12.27436. Okay, so 1 times A obviously doesn't do anything, so this tells me right now that A is equal to 12.27, about 12.27. So A right here, this side length is 12.27, okay? So we set up a cosine fraction. We use the calculator version of cosine of 64 degrees. We solve for that side length, right? Now, one more example. In this case, I actually have, well, here, I'm going to do this just so we get all three versions here. So I have a 27-degree angle marked in this triangle. For that 27-degree angle, I also have a number on the opposite side, and I have a variable now on the adjacent side, okay? So I have a number on the opposite side. I have a variable on the adjacent side. There is nothing on the hypotenuse, so there's no h's going on here. So I have O and I have A. O and A, if we think back, right, or if we look at our notes, that's tangent, T-O-A, tangent. So if I set up a tangent fraction, or a tangent of 27 degrees, right, because that's the angle I'm talking about, is 27 degrees, that must be equal to 10 over x, right, 10 over x. So again, I'm going to do the same process. I'm going to do tangent of 27 on my calculator. I get 0.509, about 0.5095. So this is 0.5095. I'm going to put that decimalized version over 1, and the other side still says 10 over x. All right? And again, it's just a proportion. We can solve proportions. I know there's decimals, but we can do it. Well, fish method here would involve 10 times 1 divided by that decimal, or we can just cross multiply and do 10 times 1, which is 10, of course, is equal to 0.5095 times x, and then to get x alone, we would just divide away that decimal, okay? So this one, where the x shows up on the bottom of your ratio, you're going to end up dividing by your decimal, okay? Dividing by your decimal version. 0.50. So I don't really need the times 1 here. It's just 10 divided by 0.5095. So if I do 10 divided by 0.5095, my x value here is 19.627, which you could round off to 0.63 or to 0.6 if you wanted, I guess, is okay. Right, so that would be my answer for that missing side length, okay? So we can use sine, cosine, tangent to find missing side lengths of triangles if we know one angle, and we can use our calculator, right? If you have any questions about any of this or want to see more examples, please reach out to me. I'd be happy to help. Otherwise, that's all I have for you right now, and we'll talk to you soon.